Does anyone have any questions about those 3 questions or the lab I had you do yesterday? Ezra looks like the most powerful person in the class. Well done, Ezra. If anyone has a horsepower greater than 2.85, come forth. Let it be known. Otherwise, Ezra is almost 3 horsepower. Which, I mean, if you compare it to actual horses, is pretty impressive. If you compare it to like a dirt bike, it's not that impressive. Or a lawnmower. Ezra's not even a lawnmower. But he's almost 3 horses, so that's pretty awesome. So I'm hearing no questions. All of you are comfortable with the concept of power. Going 1, yes, Dwayne. I know you weren't here. What would you like me to? I know you weren't here. So you're going to, okay, so you can't answer that question. Okay, but those who were here, it's always a, if you were here, are we cool with what I assigned? If you weren't here, you need to go back and watch the videos that are going to be posted later. Yes. Number 13, how much work can a 500-watt electric mixer do in 2.5 minutes? Okay, so I'm going to do what I told you not to do every class, and I'm going to cram my work in here because it's not a lot. Don't do this. Separate paper, coil book. Yes, that's bad. Bad, bad, bad. How much work? So power equals work over time. You know the power. It's 500 watts. You're looking for the work. Dividing it by the time. 2.5 minutes is how many seconds? There's 60 seconds in a minute. So 2.5 times 60 is how many minutes or how many seconds? 150, you betcha. So there it is, solve for W. Multiply both sides by 150 and you're done. 150 times, or sorry, 15 times 5 is 75. Tack on 3 zeros. You get 75,000 joules. Answer's right there. That is how you do question number 13. Okay. If you did your lab, hand it in. If you didn't do the lab, you have the handout in your notes. I will let you figure out getting that done on your own time. Good luck. May the force be with you. If you were away, yes, okay, I'll even tell you who was away yesterday. You guys need to make friends with each other. If you'd like to do the lab together. The following absences for yesterday. Dwayne, Kaylin, and David. And Grushan. Jaden, were you here yesterday? No, Jaden was here yesterday. Grushan, Kaylin, David, and Dwayne. So, Dwayne, if you'd like to find someone who's willing to help you out during tutorial, you're welcome to do that too. But you are otherwise on your own for getting that lab done. Here we go. The work energy theorem. The work energy theorem is basically, actually, it's exactly what I did this morning with my Science 10s. It is like the pinnacle of what you do in Science 10, where you're like, oh, well, the law of conservation of energy says, you know, the energy at the beginning has to be equal to energy at the end. The only thing you guys get different is you get this concept of work being done. So when I introduced to you work, I said one of the ways, I'll go up here, one of the ways that we talked about work is that work was equal to a change in energy. Well, what's a change in energy? If a change in any concept, whether it's energy or displacement or whatever, velocity, whatever, change in is always a final value minus an initial value. So work equals energy final minus energy initial. And to help this make a little bit more sense, we're actually going to add the energy to both the energy initial to both sides. And so what we're going to get, we add EI, it's going to cancel there, and we get this idea that the energy initial plus whatever work is done is going to change it so that our final energy is going to be different than the initial energy. In Science 10, you got this exact same concept, except that W term is gone. You were told that the law of conservation of energy says that initial energy has to equal final energy. And now here in grade 11, I'm going to say, well, that's not always true. You can have an initial energy, and if something on the outside pushes energy in, or if something inside pushes energy out, your final energy is going to decrease. And things that could add energy, I don't know, Batman's driving along and flips on his rocket motor. Boom, all of a sudden you get a bunch of bonus energy that you didn't have before. Or you're sliding along the ground and friction heats you up. That heat leaves as negative energy. So there's all sorts of things now that we're going to take into account that you wouldn't have taken into account in science 10. Bless you. That was perfectly timed. Your sneeze. As soon as I stopped talking and it was silent, then you sneezed. It was great. Okay, so imagine a large rock falls inside a tall vacuum chamber. For those of you who don't know what a vacuum chamber is, it's a chamber with all the air sucked out. Normally, these things are pretty small. Like we have vacuum chambers that are like yay big. They sit on your desk. The school used to have one and the vacuum pump broke, so we don't have one anymore. Most universities have these, but there is a giant vacuum chamber. It's like 3 stories tall. It's, I want to say, probably 10 meters across, 3 stories tall. 10 meters by 30 meters, big cylinder. It takes like 4 or 5 hours to pump all the air out. But when it's all done, you have a massive vacuum, and you can drop stuff in it. Like obviously you set it up, and then you leave, and then the air gets pumped out, and then you drop the thing. And it's for testing all sorts of stuff in vacuum-like conditions. So space, for example. But there's all sorts of ways you can play with this. They've actually done this with a bowling ball and a feather, just to show that in the lack of air, like if air is gone, if air resistance isn't a part of it, a bowling ball and a feather will fall at the exact same rate. If you ignore air resistance, all objects will fall at the same rate regardless of mass. So imagine that inside this tall vacuum chamber, there's a large rock. The rock is released at the top of the chamber, and it falls accelerating at 9.81 meters per second squared. As it falls, what happens to its potential energy? Because you've got this rock, right? Like it's up here. The thing starts to fall towards the ground. What happens to the potential energy as the thing falls? Up here, it had some maximum value of potential energy. Remember, potential energy is always measured from some reference point. If our reference point is the ground, what's the potential energy going to be down here? 0. So if it was a maximum up top and it's 0 at the bottom, the potential energy is dropping. At every point along here, the potential energy is getting lower and lower and lower. If the potential energy is getting lower, where's that energy going? Sorry? It's not going out, believe it or not. Because we're in a vacuum, there's no air. Because there's no air, there's no friction. So it's not going out. It stays with the rock. But what happens to it? Well, what's the rock doing after you let it go? It's starting to speed up. And so what's happening is, at the top, you had a maximum potential energy and your kinetic was 0. At the bottom, you have no potential energy, but you've got a maximum amount of kinetic energy. And if there is no air resistance, all of this turns into this. So the potential energy decreases to 0, and the kinetic energy increases from 0. And because we're in a vacuum chamber, the answer to the next question is no. No energy is going to be lost because there's nothing there to pull energy out of the system. No air means no friction. No friction means no heat is going to be generated while this object falls. And so this really simple truth is actually going to play out in a whole bunch of really interesting ways. The law of conservation of energy says what? What is the law of conservation of energy? Energy cannot be created or destroyed. Only transform, and so thank you, Dwayne, for that part. I'll finish the rest of it. It cannot be created or destroyed, only transformed or transferred. Slide that over there. There. Now it's the whole thing's on the screen. In real life, most situations involve air frictions, especially at the speeds that we're going to look at. So some energy is going to be lost. This energy lost we are going to look at as work being done. This energy, this loss of energy leaves the system as heat and sound. The generation of sound causes some energy to be eaten up. So what this means is if the law of conservation of energy says that no energy can be created or destroyed, only transformed or transferred, what that means is the energy initial has to equal the energy final. But if we take into account the fact that energy can be pulled out or energy can be pumped in, then we can change this conservation of energy to say that the energy initial plus whatever work is done, either positively or negatively, is going to equal the energy at the end. So this can either be positive if something added energy, I could also slide it up, or negative if something removed energy. And it's this W term that you wouldn't have seen in grade 10. But now we can take a look at it. It has meaning now. So the language that we look at in physics matters. And there's going to be a whole bunch of things that tell you different truths about a scenario without you really sort of recognizing it. I want to show you what a bunch of this language is. So we're going to draw a line. Oops, I wanted to hit that thing. Right there. Let's say that the track comes down and does actually hit that line. And then this roller coaster is going to be particularly awesome. We're going to say that there's a tunnel here. That goes underground. And so it's one of those crazy roller coasters that actually, goes underground, which would be terrifying. I've never been on one of these, but I know they have one at Six Flags down in California. And let's analyze kind of what's going on here. If this is you, you are a solo rider. Actually, your legs shouldn't be out. Your legs should be in. That would be bad if your legs were out. There's you on the roller coaster. There is some language here that you will sometimes see in a question. Usually when you go on a roller coaster, some of the language that they use, like they'll tell you what the velocity is. Like, oh, you're on the top of a roller coaster hill and you're moving at 5 meters per second. Like that's obvious what's going on there. You're moving. But there are scenarios where they might say something like this. You might barely make it to the top. Make it to the top. And let's say this is one of those scenarios. your roller coaster is such that you just barely, if you had been moving any slower, you would have not made it to the top of that hill and would not have made it over. What that language implies is that you have just enough energy to make it to the top, and for a split second you might actually stop. And if that's true, then how we analyze this situation is we say that at the peak there, and that is the peak, the potential energy is a max value, whatever that is, and if you barely make it, the implication there is that your kinetic energy is 0 at the top. You have just enough energy to bring you to the top. You might hang there, and then gravity pulls you down the other side. That language here, barely, implies that kinetic energy is equal to 0. And off we go. We are going down the hill. Here's the U. And it's fun, so your arms are going to be backwards. Who rides a roller coaster and put their hands in the air? I don't either, because I'm scared of roller coasters. But I've been made to go on roller coasters by cute girls I had crushes on, and so you can't admit that you were afraid of the roller coaster, so you get on the roller coaster because, you might have a chance. You get on the roller coaster and you hang on for dear life. But if you like roller coasters, this is how you ride. If we ignore friction, let's say we're riding the roller coaster in a vacuum. If we ignore friction, what that means is the potential energy is going to drop, the kinetic energy is going to rise, and if you add these two values together, what should they be? They're not going to be 0. Yes, they're going to equal, they will always equal whatever this max possible value was, if we are able to ignore friction. How? I don't know. It's a terrifying roller coaster that's been like greased up like crazy and you're just sliding around like a mad person. If you're able to ignore friction, that will always be a max. At this point right here, if this is ground level, we'll call that h equals 0. What's true right there? Kinetic energy is at a max, and potential energy equals 0. Everywhere along the trip, you cannot get more energy than you put into the system. So then back up here you are. If there's no friction, are you going to make this hill or not? You should, because it's shorter than the tallest hill. So at this point, you should have more than enough energy to make it over this hill. Again, assuming friction is 0, there's no energy being lost. This is a smaller hill than that. You're absolutely going to make it over. So at this stage, you will have some kinetic energy. We don't know what it is, but we know it's not 0. And at this stage, we are also going to have potential energy because you're above here. We don't know what it is, but we know it's not 0. We can say that this is going to be less than max, more than 0. We can say that this is also going to be less than the max, more than 0. And if I added these two things together, what should the result be? The max possible value, whatever it is. This is where things get interesting. Let's say you're actually, in here. Don't want to put your hands up too high because you might hit the ceiling. That would be terrifying. Your hands get sliced off while you're on the roller coaster. That'd be awful. Let's pretend that doesn't happen. But now you're underground. Let's talk about the math here. What can you tell me about the potential energy and the kinetic energy? Let's talk about the kinetic first. If you are below this point right here, what does your kinetic energy have to be? No, you're definitely moving forward. Not the kinetic energy won't be negative. But if you're below, if you're somehow lower than this point right here where you have the maximum kinetic energy, it's going to be max plus something. When max plus something, it's going to be more than max. This is going to, oh, no, kinetic energy. We want maximum value plus something. We don't know what it is, but you're actually given more energy at this stage than your maximum possible value. That's really weird, because you should never have a maximum value of energy that's greater than you were given to start. So how do we compensate for that? If we said that this green line represents height 0, what's your height down here? It's going to be negative. Who said that? Mary? Yeah, it's going to be negative. And if your height's negative down here, what's that going to do for your potential energy? Got to be negative. You're now below what we called 0. You're going to have a negative potential energy. Negative what? I do not know. Actually, I don't know exactly, but negative something. Negative what? How is it going to be related to this value right here? Sorry? Yeah, it's going to be opposite. It's going to be the negative of whatever you added here. So if you added question mark to get your potential energy, you're going to have negative question mark, because you still need these two things to add together to give you that maximum value you started with. These two values always have to line up, regardless of what happens in between. And so we compensate for the fact that we now have a larger kinetic energy than we should by having a negative potential energy, so that when these two add together, you still only have the same total energy you started with. It's kind of a weird way to think about it, but the math works. And that's really all that matters in physics, is if the math works. Okay, so questions so far about conservation of energy. This is way beyond what my grade 10s did today. Bless you. Are we comfortable with everything that's been written on this? And if you're not comfortable, can you at least accept it to the point where we can move on? This is your chance to resist. Colden's nodding his head. Colden says we're good. Here we go. Flip the page. I'm going to do 4 examples. And then I'm going to leave one for you to do. And then I'm going to give you a bunch of work to practice. Here we go. You have a 56-kilogram diver runs and dives from the edge of the cliff into the water, which is located 4 meters below. If she's moving at 8 meters per second the instant she leaves the cliff, find the speed at which she enters the water. Seems reasonable enough. Let's take a look. So let me draw it for you. As often as you can, draw out the scenario that's happening to you. You have your cliff. Here's the water. Because if there's no water, then this isn't a cliff jump, it's something else. And we've got someone sprinting. They're hoofing it towards the edge of the cliff. And when they reach the edge of the cliff, they do this. They jump. And they're flying through the air. And at this point, their velocity is equal to 8 meters per second. What's going to happen? This is a problem you've seen before. How have you seen this problem? Where have you seen this problem? In where? In kinematics. This was the last thing we looked at. This is a projectile motion problem. This person is being launched straight off a cliff, sideways. They're going to impact on the ground. If this was the question that you were given back in February, you'd set this thing up and you'd say, okay, here's review for your final. I've got some X directions, I've got some Y directions, I've got a velocity in the x direction of 8. I've got an initial velocity in the y direction of 0. I've got an acceleration of negative 9.8 meters per second squared, yada, yada, yada. Do I know the height of the cliff? Yes, I do. It's 4 meters. And you could set it up this way, and you could solve this problem like a kinematics question. Or, let's not do that, because if I remember back to February and March, you guys didn't really enjoy that. So let's look at an alternative way to analyze that exact same problem. So this is the kinematics way to do it. Let's do it with energy. Let's analyze the exact same scenario with energy. Every question starts this way. Energy initial plus work equals energy final. We start with the law of conservation of energy. And the only way at this stage to actually tackle this problem is to assume that we can ignore the air. If we ignore air, it means we can ignore friction. She's not moving fast enough to have a measurable amount of heat build up on her. 8 meters per second. I mean, that's pretty quick. Let's be honest here, 8 meters per second. She's running at almost 30 kilometers per hour. I mean, the world record Usain Bolt is 45 kilometers per hour, but she's definitely an Olympian. At the very least, she's really good at track. But she's not moving fast enough to really notice heating up. And so what can we do here? If we can ignore the air, what can we ignore in conservation of energy? Sorry? If we can ignore friction, then which of these three terms can we toss out? We can ignore friction, and she's not wearing a jetpack. So we can ignore this outside energy term. That's what work is. Work is energy that came from the outside or is being pushed to the outside. This term we can ignore as 0. So for now, if we're going to analyze this using energy, we have to take a look at what's going on. At the beginning of the problem, what kinds of energy does she have? She's got kinetic energy because she's moving. So I'm going to use green for this. Kinetic energy initial plus. Does she have any other form of energy at the beginning? Sorry? What kind of potential? Sorry? Yes, but what kind of potential energy? Spring or gravity? Those are the two kinds we've looked at. Is there springs in this problem? So then it's gravity. You got to be specific. Potential energy gravitational initial plus 0 equals, when she hits the water, what kind of energy does she have? Is she moving when she hits the water? Presumably. So there's going to be some kinetic energy at the end. Now, she only has potential energy if this isn't our reference point. By measuring that the height of the cliff is 4 meters, what are we calling 0? The water. We're calling the water level 0. So if this is height 0, does she have any potential energy here at the end? When she hits the water, 0 height. So there's no potential energy at the end. So this is the expression now that we're going to use to solve this problem. And now we can fill in each piece. We know that the initial kinetic energy is going to be 1/2 mv initial squared. The initial potential energy gravitationally is going to be mg height initial plus 0 we don't need to include, and that's going to be 1/2 mv final squared. And now all we have to do is fill this in with the information we have in the question and solve for whatever's left. We know her mass is 56, so let's plug that in. 1/2 times 56, we know her initial velocity. What is it? Up here on top of the cliff, she's moving at 8 meters per second. It's going to be a half times the mass, 56, times 8 squared, plus 56 times g, which is 9.8, times the initial height, 4 meters, is going to equal 1/2 times 56 times v final squared. And now we can find what Vf is. To make your life a little bit easier, as you're solving these things, you can cram this whole piece into your calculator. This whole thing is going to condense down to 0.5 times 56 times 8 squared plus 56 times 9.8 times 4. Boom. This value right here is 3,987.2 equals, well, half of 56 is 28, so that's going to equal 28 V final squared. If the algebra is something that you struggle with, simplify it where you can. Do all the math on one side, simplify the right-hand side, and now we're going to isolate for VF. We're going to divide by 28, we're going to divide by 28, boom. We're going to square root both sides, and you're going to find that the final velocity of our diver as she enters the water is going to be 11.9 meters per second. Which makes sense. She should be moving faster than she started because she was moving at 8 meters per second and then gravity added to her velocity. This is I think anyway, correct me if I'm wrong, I think the energy way to do this is substantially easier than the projectile motion stuff I had you guys do back in February. Comments, questions, concerns about question 1? Okay, if there are no questions, let's look at question 2. Stop me at any point if I can clarify things. Okay, let me zoom in. Question 2 looks like this. A car with a mass of 1,500 kilograms, and that's not a small car, has a velocity of 12 meters per second and accelerates to 25 meters per second. What is the work done? So, okay, we have a situation where we've got a car. It's not a very fancy looking car. Maybe it's a van. It's moving. The velocity here is 12 meters per second. And just to give that some perspective, 12 times 3.6 is 43. So we're going just below speed limit here. And the van realizes, maybe they were on their phone while they were driving. They weren't paying attention to the fact that they'd slowed down. And they were like, oh man, I got to speed up here. Boom, boom, boom. The speed lines get bigger. And now we realize that their velocity is 25. Again, to put that into perspective, now they're going 90. So the speed limit on the Abbey Mission Highway, plus 10 kilometers. I'm pretty sure that's 80. So they realized they were going too slow, and now they're speeding. Now, for this to happen, something had to do work. Something had to add energy to the system. What kind of energy did the car have? Well, again, we'll start this way. Energy initial plus work equals energy final. What kind of energy did the car have to start? Kinetic. If the car doesn't change its height, do we have to talk about potential gravitational energy at all? No. The car was on the ground, it's still on the ground hasn't moved. So let's assume that this is what we're going to call height equals 0. We can ignore gravitational potential energy here. At the end, there needs to be kinetic energy. It's still moving. But this kinetic energy is going to be bigger than this kinetic energy. If this one is bigger, if this one is bigger than this one, that means something somewhere had to pump energy into the car to cause it to accelerate. Where'd the energy come from? The engine. Burning more fuel. You push the accelerator, you allow more fuel to flow, more fuel goes boom, you go faster. Very simplified explanation of an internal combustion engine. But that's really all it is. Something somewhere had to give you more energy to speed up the car. How much? Let's take a look. Kinetic energy initial. 1/2 mv initial squared plus this work term. We have to include this work now because work is being done. Equals 1/2 mv final squared. Let's go up here because I'm running out of space. We can fill in these values for masses and velocities because we've got all those. 1/2 times 1500 times the initial velocity of the car was 12 squared plus work is going to be 1/2 times 1500 times 25 squared. How much work was done? What do you get? Punch this into your calculator, tell me what happens. It's kind of a ridiculous number. How much extra energy did you suck out of that gas tank? If you have a number, call it out. When you have a number, just call it out. Ooh, that's a bigger value than I got.
Oh, wait, okay, sorry.
You added them together?
Yeah, I went the wrong way with it.
Yeah, when you move to get work by itself, you have to subtract this whole thing over. So it's going to be 0.5 times 1500 times 25 squared minus this whole piece. 0.5 times 1500 times, oh, that's not 1500, times 12 squared. It's still a large number. 360,750 joules is what you should be able to get. You should all have your calculators out, making sure that you can get these values. Okay, questions about what was done? Let's do another one. Again, the only way we can actually tackle these problems at this stage, given what's here, says find the speed at the top of the second hill. We have heights and velocities, is to assume no friction, heat, or sound, which we know is not true. But we can't do the problem unless we ignore those things. So let's ignore them. Okay, so there are two ways to do this problem. When I introduced or reintroduced gravitational potential energy to you, I told you you could put, it's a reference point. You can decide what you wanted to call zero. Like when I was demonstrating it, I had my pen above the desk, and when the pen was above the desk, we said the desk was zero. And then I moved the pen over here and I said, okay, well, what's zero now? You said the floor. If I hold the thing out the window, then what's zero? The ground, 3 stories down. So what you call zero is entirely arbitrary. And I want to show you that with this example. if you were looking at this problem, you've got a height of the first hill measured from this point right here. You've got a height for the second hill measured from this point here. You would be tempted to call what 0? What does your gut tell you to call 0? That line. Seems reasonable. Okay, if we call that height 0, what kind of energies does our object have at the beginning? Well, we're going to have energy initial plus work equals energy final. What kind of energy does our object have at the beginning? It's got gravitational potential because it's at some height, and it has kinetic because it's moving. We're told it has a velocity of 2 meters per second there. This isn't a barely made it over the top. You're over the top at 2 meters per second. So you've got some kinetic energy there. We're ignoring friction, heat, and sound, so this term is going to be 0. What kind of energy do you have right here? At the top of the second hill? The same. You're going to have gravitational potential energy, finally, plus some kinetic energy, finally. And we could go ahead and we could fill these out and we could do it. Alternatively, what if we didn't call that blue line 0? Is there another point that we could justifiably call 0 that would help us out here a little bit? Because it's totally arbitrary. The height that you define to be 0 is entirely up to you. And there are good and bad places to put it, yes. If you put 0 right here, how does that change things? You're absolutely right. That's the place to put it. How does that change things, Emma? Your intuition told you that that was a good idea? You could put it up the top. You can put it anywhere in between. Sure, you wanted to put it right there. That is the other place to put it. If you put it there, let's see what happens. First of all, let's start with energy initial plus work equals energy final, and we're still ignoring this. By putting energy initial there, by putting height 0 there, you still start above that green line. But how high are you now above the green line? You're not 20 anymore, you're not 10. This is 12. We moved 0 up 12 units. So this distance is now what? 8. This distance here is now 8 meters. Because you moved this blue line up 12, 20 minus 12 is 8. By putting that guy there, you can say, okay, at the beginning, I'm 8 above that green line, so I still have some potential energy, gravitational initial. I still have kinetic energy right there. That work term is still going to be 0, but if this point right here is 0, what kind of energy do you have at that point? That's the only kind of energy you have right there. If this is height 0, do you have any gravitational potential energy? No. We just have to assume kinetic because we're being asked to find how fast we're going there. So by moving where you put 0, you can get rid of one of these potential energy terms. If you'd put 0 up at the top, you'd have no potential energy initial. But then everything would be measured down from that line. With a clever placement of this, you can remove some of the algebra. And I don't know about you, but I think getting rid of some of the math can make everyone's life a little bit easier. And the results are going to be the same. If we just plug these values in, I'll show you what this looks like. We don't have the mass of the roller coaster, and in this case, that's okay, because if we look at what's going on here, this is going to be mgh initial plus 1/2 mv squared initial is going to equal 1/2 mv final squared. What can we do with the mass? If it shows up in every term, we can divide it out. Divide by the mass. Gone, gone, gone. We can do the same thing over here. If we did it this way, we'd have mgh initial plus 1/2 mv initial squared equals mgh final plus 1/2 mv final squared. And the mass would divide out there too. Doesn't actually matter what the mass of the roller coaster is. So now we can go ahead and we can find the speed of that roller coaster. G is 9.8. And if we look at the green one, the initial height isn't going to be 20, it's going to be 8, the distance between the top and the line that we're calling 0. So 9.8 times 8 plus 1/2 2 squared is going to equal 1/2 v final squared. This is 78.4 plus 2 equals 1/2 v final squared. And I'll give you, for the sake of time, I'll give you the value here. VF is going to equal 12.7 meters per second. And if you did it this way, assuming you didn't screw up the algebra, you get the exact same value. The only difference is this initial height and that final height aren't going to be 8 and 0, they're going to be 20 and 12. Questions, comments, concerns about what I've done there? Okay, then if there are no questions, flip the page. I got 2 more examples. Okay, a force of 10 newtons acts on a 2 kilogram roller skate initially at rest on a frictionless table. Okay, well, here we go. Let's draw it. There's our table. That's supposed to be level. For those of you who don't know what a roller skate is, it's like a shoe with wheels on it. It's not like roller blades. Roller blades are terrifying. I mean, roller skates are terrifying too. It starts at rest. You push on it for a while. And now it's going faster. At rest means VI equals 0. It says that a force of 10 newtons acts on the 2 kilogram roller skate, initially at rest on the frictionless table. The skate travels 3 meters while the force acts on it. It's interesting. Why would they give us that piece of information? And what is the final velocity? We're looking for this. Why would they give us this? A 10 Newton force acting for 3 meters. That's the work. Work equals a force times a distance. The wording of the problem here is trying to prompt you to see, hey, we have a work term here now. So now when we go ahead and look at this thing, energy initial plus work equals energy final, we have something to put in here now. Do we have any initial energy? Answer that question and you can go to the washroom. Do we have any initial energy? It's sitting on a table, not moving. No, we do not. There is 0 initial energy. You bet. Plus, now we do have work. we're told that we have a force acting over a distance. You need to recognize that as the definition, the first definition I gave you for work. So we're going to have a force times a distance acting here. And we're asked to find the kinetic energy at the end. So force times a distance equals 1/2 mv squared, mv final squared. And now we can go ahead and we can plug this in. This is a quick example. The force is 10 newtons acting over 3 meters. Equals 1/2 the mass of the roller skates 2, v final squared. Oh, this is beautiful. 10 times 3 is 30. Half of 2 is 1. So 30 equals v final squared. V final is the square root of 30. Which I'll tell you is 5.5. The whole point of this example is to show you this. The wording of the questions are going to push you towards seeing particular truths. Questions about what I've done there? Okay, if there's none, let's do one more. Several students are pretending that they're in the jungle while playing in Ravine Park. Do not go play in Ravine Park, but let's pretend that you have. You're playing in Ravine Park. Ravine Park is a scary place to play if you've never been in there. A friend of mine stubbed her toe on a needle in there. Not a good place to hang out. She had to go to the hospital and do the AIDS test, like that whole thing. Don't go play in Ravine Park. Students are playing in Ravine Park. Here we go. We've got the ground. They suspend a rope from an overhead tree limb. Now, we don't have very many good trees for this, but let's say we did. Here's a tree. Here's the tree. Big tree. Big tree. I'm not an artist. We need Dana for this. And this particular tree has one random branch. Bam. There it is. One random branch. And from that random branch, students have hung a rope. A student of mass 70 kilograms. So this might be someone like, oh boy. I don't know. 70 kilograms, like 150 pounds? Yeah, sure. Let's assume Brad is 70 kilograms. You're not. You're probably, I don't know. Oh, you weighed yourself yesterday.
It's like 64.
Cool. Let's round up. Let's call 6470. Brad, you're going sprinting through Ravine Park. If you're running, Brad, at 8 meters per second and you grab the rope, you're going to swing up. How did I draw this? You got your hands, and then you got your knees wrapped around that thing. There you are, Brad. You're swinging through the air in Ravine Park. I would never recommend this. How high in the air have you gotten? At the top part of that swing. Now, you're not moving fast enough for the air to really heat you up. So we can assume that there's no air resistance. 8 meters per second is not nearly fast enough for air to be a thing. So we can ignore it. So then, Brad, what kind of energy do you have at the beginning? At the beginning.
Oh, no, it's 0, right?
At the beginning, height 0. Presumably, we're measuring from the ground up. So presumably, that's going to be height 0, which means if we look at energy initial plus work equals energy final, no air resistance means this is gone. And yeah, you're right. Kinetic energy is the only energy you have at the beginning. At the end, you're at the maximum point of your swing. What kind of energy do you have at the maximum point of your swing? gravitational potential, and that's it. Because at the top part of your swing, you're not moving. So potential, gravitational, final. So let's plug it in. Half mv initial squared equals 1/2, nope, equals m, oh, that's an m, believe me, that's an m, gh final. That's an important line to write for reasons. So let's plug these things in. Half times 70, because we're rounding up, times 8 squared equals 70 times 9.8 times your final height. Brad gets how high off the ground? What's the value? As soon as you got it, let me know. Thank you. Hold on, no. 3.2 what? What's the digit after 2? So that should be 3 point. Thank you. Okay, so here's part B. Who is a student that, so Brad said he was 64 kilos, we rounded it up to 70. Can anyone volunteer the fact that they are less than that? I don't know, I don't care what the number is. Let's just say that they're less than that. Who wants to volunteer as being less than 70 kilos? Harleen, you were less than 70 kilos when you weighed yourself yesterday. Cool. So here's the question. Harleen is also in a ravine park with Brad. How fast does Harleen have to run to reach the same height Brad did? Without doing any math, tell me how fast she has to run to reach the same height. I want to show you something cool. Look at this line right here. What can we do at this line? What could we have done? Sorry? We could have divided out the masses. The masses cancel. So does it actually matter what mass the runner is? No. If Harleen and Brad ran at the same speed, heck, if I ran at the same speed, if all three of us ran at the exact same speed, 8 meters per second, I'm 100 kilos, Brad's 70 kilos, all we know is that Harleen is less than that. It doesn't actually matter. The masses cancel. We're all going to reach the exact same height, assuming we can all reach the same initial velocity. I hate running, so I wouldn't count on me. But, you know, Harleen and Brad look like they could enjoy running. They could be one of those people. Masses cancel. So speed is the same. It does not matter what the mass of the runner is, as long as they're able to reach that velocity, they will reach the same height. Okay. I got a list of questions I want you to play with. Here they are. This one, ooh, interesting, yes. This one does not have the answers with them, so I will give you those tomorrow. Here you go. I'm going to create a list up at the top here. I want you to do the following questions. I want you to do questions 3 to 5. I want you to do questions 8, 9, 12, 13, 2, 3, 5, 6, and 6. If you go through them in order, you'll see what I mean. The numbering restarts right here. And then there's some questions on the back page here too. This is the second number 6 I want you to do. This is the 2, 3, and, oh, hold on. Nope, I lied. There is only one number 6. Yes, I want you to do this 2, 3, 5, and then number 6 back here. You got some time? Play with it. You're only going to figure this stuff out if you spend the time working on it. Let me know how I can help you on your Market Set Giver.